Hi, welcome to MEN3 689, where I'm going to talk to you a little bit about modeling and parameter identification for soft materials. So first, I want to talk to you a little bit about what is meant by a soft material. Soft material, things like polymers, biomaterials, also things that show up interestingly in essentially they are actually highly deformable materials. And there's a lot of interest in modeling these kinds of things for a variety of contexts. One is, of course, from a practical engineering point of view, where you want to do different kinds of materials and you want to find out what's going to happen. Maybe you want to make artificial tissue, or you want to figure out when something is going to rupture or break, or you're making some new plastic bag or something like that. The other interesting area is in virtual reality. And interestingly enough, a lot of image processing turns out to be closely related to the mechanics of soft materials. So I'm going to write, and this connection is interesting because there is a deep connection between things like Bezier curves, cubic splines or splines, and other graphics objects are closely related to things in mechanics and actually structural mechanics. Okay, so that's the idea. So the first item that I want you to become familiar with is what is called a vector space. Okay, so sounds, you're like, what do you mean? I mean, I know what a vector space is. So some of you may not. So let me ask you a following question before you proceed. Let me ask you, what is a toothbrush? Hey, humor me. Don't, just tell me, what is a toothbrush? So what I want you to do is pause, think about it, and replay this video, and you can ask yourself, what's a toothbrush? Okay, so did you pause? Did you think about it? Now let me share with you the possible types of things you might say. One is what a toothbrush looks like. What I mean by that is, if somebody asks you what's a toothbrush, you might say that it's a object with a long handle and bristles at one end. Or you can say what a toothbrush does. So a toothbrush is something that's used for cleaning your teeth. Notice that the first one is what it looks like, or is what is called an embodiment. You are describing its appearance, its characteristics. The second thing is what is called functionality. That is, it does not tell you what it looks like, but it tells you what it does. All of mathematical abstractions are like that. The idea behind most of mathematics is to describe the functionality of different things, not what they look like, but what is it that they do. Right? So this is a very key idea behind mathematics. So we are talking about functional characteristics of things and not what they look like. So for example, a plus sign looks like this, but if I add 3 and 4, that's one functionality that tells me it's 7. But if I adding 2 line segments, it's a geometrical process that's also called plus, but we are not really adding numbers. No, we are doing some, move one vector, move one arrow to one end and then add another one, so on and so forth, right? So different kinds of structures, the same shape can mean different things. Okay, so I want you to understand that. So now we come back to what is meant by a vector space. So if I ask you what's a vector and you answered something with magnitude and direction, this is an embodiment. This is not functionality. The correct question we have to ask is, what can we do with vectors? Right? So when we talk about vectors in mathematics, we don't care what it looks like. We only care what it does. So what can we do? So things that we can do is, or one, I can add them. This is usually referred to closure under addition. So imagine you have a basket or a set of objects called vectors. If you take two of them, A is the element of that set, B is an element of that set, then A plus B must be an element. Okay, so that's item number one. The second thing I should be able to do is scale them. That is, if A is an element of that set, alpha times A must also be an element of that set. Where alpha is any scalar, especially, I mean, the kind of scalar we are talking about that we care about is real numbers or maybe complex numbers. You can even have, like, you know, binary numbers and so on, but we are, for our purpose, we are not very much interested in that. Okay, so I should be able to scale them, and then I have all kinds of nice laws. So when I add them, I should be able to do A plus B equal to B plus A. This is commutativity. Order of addition should not matter. Okay, and alpha A plus B equal to alpha A plus alpha B. All of this is common sense. If you don't have them, you will get some strange behavior. The one thing that's come somewhat surprising and which is not a common sense is that there should be something called a zero. Which means, and the zero should have some very nice properties. A plus 0 must be A, and corresponding to every element there should be a negative element, which if you add it must give me 0. Okay, so what I'm saying is, I am not going to do a formal definition of vectors, but there are certain key properties. One is it should be closed under addition. The second thing is I should be able to scale it and it should still belong to the set. The third thing is addition should be commutative. Addition should be, this is distributive over scalars, and I can also do distributive. A plus B plus C is the same as A plus B plus C. Okay, and the last thing is 0 element must exist. That is, A plus 0 must be 0, A plus minus A must be 0. Okay, so anything which has this functionality will be called a vector space. So the set of line segments. So if I look at a set of line segments, so that's our arrows. The 0 is just a dot. Okay, addition is put the line segments end to end, and the resulting line segment, this is A, this is B, this is A plus B, and the parallelogram law of addition, you know all this stuff, right, is the commutativity property. Now this is B, this is A, so what does it say? A plus B is the same as B plus A, right, and A plus 0 is the same. Scaling is just making the vector longer. right? Conventional vectors have all these properties. But there are a lot of unconventional vectors that also have the same properties. For example, if I look at set of all functions, f of x from for x between minus infinity to infinity. Okay, is it clear that if I take two functions f of x and add it to g of x, I'll get another function h of x, right? I can scale it, I can do all this fun stuff. You know what I mean? So that's an example of a non-standard vector space. By the way, it's not as non-standard as you think. What do I mean by that? So suppose I give you a standard vector, like what is called a column vector, 3, 4, 5, 7. Right? This is a 4-dimensional vector. Can you see that? 1, 2, it has 4 components. Right? And I can draw a histogram. Instead of drawing it like that, instead of drawing an arrow and a line, I can draw a histogram. So I can say 3, 4, 5, 7. Can you see that? And I can draw a histogram like this. You're with me? This is nothing but a step function. You're with me? So any vector becomes a step function. This connection is important because later we will see that if to take any function, all I can think of is it's like a lot of step functions. So I can do, like if you give me a function like this, I do, see what I mean? So not surprisingly, functions behave like vectors. That is, they have the same kind of, you can do the same things to functions that you can do with vectors. Very good. But you are thinking, okay, what's the big deal? Perhaps you knew all of this. Now let's look at a different one. Think of a differential equation. So let's say I have d squared y dx squared equal to minus 3y. So would you agree that y equal to sine of root 3x is a solution to this? Y equal to cosine of root 3x is a solution to this equation, right? Agree? How about some linear combination? A times sine root 3x plus b times cos root 3x. Is that a solution? Yeah, you're thinking yes, no? Notice that I have scaled the two things. I want you to understand that the set of all solutions to a linear differential equation is a vector space. That is why you can mix and match. Okay, so that's an example of a vector space, right? So you got the idea, right? So it should be closed. So roughly speaking, if A and B are vectors, alpha A plus beta B must also be a vector. For any scalar alpha and beta. So for example, if I put alpha equal to 0, beta equal to 0, then I should get alpha A plus beta B must be equal to the 0 vector. And this should also be in this set. You're with me? So the idea is closure. You should not be able to step out of the set. Imagine you are your vector island, right? Like you cannot be voted off the island. So you have, everything has to be inside the island. You cannot step out of it. Okay, so that's the most important thing, and you should be able to mix and match. So the key property is mix and match, and order does not matter. There is no hierarchy, there is no priority. You cannot, you can mix and match them any way you like. Okay, if you remember those two things, you can find lots of interesting vector spaces. Okay, we are done with the lecture. What I want you to do is now test and tell me whether these things are vector spaces or not. One, set of all rotations. Is that a vector space? And you have to figure out what do you mean by adding rotations and what do you mean by scaling rotations. Okay, think about what those two things mean. So vector or not. If they are vectors, you should be able to say why. If they are not vectors, you should be able to say why not. What rule are they violating? Second thing is set of all continuous functions between x equal to 0 and x equal to 1. Is that a vector space or is it not a vector space? 3. Set of all colors. Is that a vector space? Is that not a vector space? What do you think? How about 4? Set of all functions such that f of 3 equal to 0. Is that a vector space? Is that not a vector space? Fifth one, set of all functions such that f of 3 equal to 0, f of 4 equal to 1. Right? So in order to define a vector space, you need a couple of things. One is you need a rule for belonging to the set. Who gets selected to be in the set? Who gets voted into the island? Okay, that's the first thing. So in this case, the selection criterion is here. That's item number 1. Second item is there should be a common sense way of adding them. Okay, meaning that if I add two things, they should be in the set. If for every element there should be a cancelling element, a negative element. I should be able to scale them. I should be able to reorder them in any way I want. I should be able to commute them, or I should be able to distribute them any way I like. And there should be a zero element, which means that there should be an element which does nothing. Okay, so imagine these things. When we meet for class again, we will talk about whether these things are vector spaces or not. And if you have questions, write them down so we will discuss it in class. Thank you.